Hey guys, just having a look at this inequalities, but using integration. So the way that they set these up is they tend to ask you to do some sort of graph, and they form the inequality using areas. So in this particular case here, you can see they've set it up very nicely for you. They even say by considering the area under the curve, which is a bit of a dead giveaway, but even without that bit, the A and the B part definitely suggests this method. So they've just got the curve y equals 1 on x. They've asked you to add a generic point n, and then the point before it and the point after it, or one before it, one after it. I'm giving you those. So I've just got the details up on there. Find the tangent at the curve at that one, pretty straightforward. It's just here. Okay. Now this is the bit that I want to talk about. Inequalities, when you look at areas, there's two things you should remember. First of all, areas can be found using trapezium or normal shapes, but of course can be found through integration. And the process of integration also conserves inequalities. So if you integrate both sides, and you have function, one function is greater than the other, then you integrate that. The result of that integral will also be conserve that inequality. So in this particular case, it's just straight up comparing areas, but very often it can start with comparing functions, and then you integrate those functions to get the inequality that you want. So keep an eye out for those. But this is the one that I'm talking about here. So essentially what I ask you to do is to prove this. Okay. Now it's a double-barreled integral. Okay, so you've got something in the middle and then something that is bigger and something that is smaller. So it's said by considering the areas. So we're going to look for what's in the middle. So we need something that's going to be in between a smaller area and a larger area. Okay, so it sort of sets it up like this. Now, because of the information they talk to us about already, we sort of know which ones we're talking about here. So here's the diagram, and just I've drawn in a couple of extra things here. The middle one, it turns out, is going to be the area underneath the curve. So here in orange, okay, right there. And then the one that's smaller is going to be the area underneath the tangent. So because this is concave up, the tangent's always going to be below. And so the area in between the same limits, which of course we're going to use the same limits, the area underneath the tangent is going to be smaller than the area underneath the curve. Then you're looking for a bigger one. Now, for the same reason, if you take a coordinates one before and one after A, then the chord that joins those, so the chord BC in this particular case, is always going to have a larger area underneath it than the curve will, because the curve is concave up, and so it'll always be above. So the question sort of led you down this a little bit, but the important thing is to remember that you've got to have something in the middle here, and then two things, one that's always bigger and one that's always smaller. The important part of using the curve 1 on x here is that it's concave up. In the region we're talking about, and so we know the tangent is always below and the chord is always above. So then I just did these individually, and it works out to be pretty easy. If you take the area underneath the tangent here, I just did it using integration, you end up with 2 on n, which is unsurprisingly exactly what we need. If you take the area underneath the curve, that's 1 on x between those limits, you get log of n plus 1 over n minus 1, again, exactly what we have. And then the area under the chord. Now I could find the equation of the chord and use integration, but of course it does make a trapezium. So to find the area of a trapezium, we need the distance between the two parallel sides. Okay, that's h. And then you need the length of the two parallel sides. So that's a and that's b, or the other way around, doesn't really matter. So the length of a in this particular case and the length of b are the y coordinates of b and c, and h is the difference between their x coordinates. So I just wrote that down here. A and b, the parallel sides, are their y coordinates. The distance between their x coordinates is h. It ends up there, and unsurprisingly, it gives us exactly what we like. But what we have proven so far is this statement in black. That 2 on n is the smallest area, 2n on n squared minus 1 is the larger area, and so the log of n plus 1 over n minus 1 must be in between those two. The question, however, adds less than or equal to. Now, this is where it gets very Fourier-nitty, if you like. We've got to think about, well, why do we have that equality there? And that's because as n approaches infinity, so if n is quite large, then the tangent itself will be very, very close to the curve. Infinitely close, in fact. And so as n approaches infinity, we actually get an equality of those two things. The other way, however, because you're doing a movement always of 1, so the 2 points are not getting any closer to each other, you will always have a trapezium that is larger than the area underneath the curve. so that we don't get inequality on the right-hand side there. So to get your full marks for this one, you would need to address why one of them suddenly becomes equal to, one of them becomes, and one of them stays. In the end, guys, these are small questions. They're not a very large part. They tend to have a build-up of graphing and those sorts of things. So if you do get those double-barreled ones, or they do lead in with some sort of graphing and then go to an inequality, keep an eye out for areas underneath curves.